Hello, Physics Nation. My name is Nate Larmond. It's At Home Science Part 3. We're trying to find the mass of this stick, but you don't really need a fancy 2-foot long piece of balsa from the craft store. You could use a stir stick. They give you these free at the hardware stores, Lowe's, Depot, Ace, Walmart, or, a ruler. You could use that for your lever. What's the mass of the ruler? Or the pen, what's the mass of the pen? Anyway, you need some kind of solid lever. I have the fancy balsa wood because it's more dramatic. But any stiff lever that you can hang and apply a torque to, or two torques actually, will work great. All right, so that's the puzzle. What's the mass without using a triple beam? And I guess I should start explaining torque. So, try to balance something on your finger. There's a twisting force that's tending it to rotate in that direction. All of the weight of the pin on this side is causing it to rotate this way. Let me see. That is clockwise for me, negative z. All of the weight on this side is tending it to rotate counterclockwise. That is positive z. But the clockwise torque plus the counterclockwise torque equals 0 because you can see there's no angular acceleration. This is rotational equilibrium. So that's where it all starts. If there's no acceleration, the system is in equilibrium, except now we're talking about rotational equilibrium. Let's see. Let's talk about what things affect torque. Well, like I said, force. So let's do the weight of this marble. And let's use the stir stick as our lever arm. So my fingers are the pivot or the axis or the fulcrum. And now that distance right there, hang on, where's my ruler? That distance right there in between the fulcrum and the applied force, the weight of the marble, is the lever arm. So all you do is you take this force and multiply by that distance. That's the torque. Now this force and this lever arm are perpendicular. It gets a little bit more complicated than that, but check it out. As the lever arm increases, I have to apply more and more pinching force to increase the friction so that the stir stick doesn't accelerate. All the way out here, I have to apply quite a bit of pinching force so that the torque applied by the marble is counteracted by the torque applied by my fingertips. There, the marble won the little torque balance. Okay, if you don't want to work with a marble for a mass standard, water is a fantastic mass standard. This is America, so a gallon of water weighs about 8 pounds. Let me see, what would that be? 8 multiplied by 4.45 is 35.5 newtons. So if you don't want to, use a little stir stick, if you want to put it on, a branch outside, you can generate a lot of torque. If you start hanging, 35.5 newtons. So again, there's the lever arm. My pinching finger is the pivot, the axis, the fulcrum, the middle of the rotation. And that distance right there in between the force and the pivot is called the lever arm. And as the lever arm increases, the torque increases. And even though this gallon of milk, this milk jug is empty, you can actually see the torque increasing. It's not because of the increasing force, it's because of the increasing lever arm, the distance in between the force and the pivot. You can see the bending stress. That's why these things are so expensive, because balsa is an amazing material, very flexible, very resilient, and light, very light. Each one of these sticks costs like $1.50 at Michael's, but they're well worth it. I should be sponsored by Ace and Lowe's, Michael's. Anyway, here's the puzzle. Hang not a milk jug, woo, but some coins. Coins are amazing mass standards. The US government makes them to an amazing precision. I think quarters are 5.67 grams, but I'm not sure. Whoops. So this thing is falling out of equilibrium. The torque provided by the quarters is now much greater than the torque provided by the weight of the stick. I don't know if you can see the little mark, but that black mark is the CG of the stick. So all you have to do is adjust the lever arm. I'm actually adjusting both lever arms. As the lever arm to the quarters decreases, the lever arm to the stick increases. So you're actually playing with two variables at the same time. And oh, I've almost reached rotational equilibrium. Oh, there it is. It's magic. All right, so that, the distance in between the fulcrum, hang on, let me get it right on camera. That, the distance in between the fulcrum and the quarters is one measurement. You just put the ruler right there. And then the more annoying one is the distance from the CG of the stick, where's my black mark, right there, to the fulcrum. That lever arm is gigantic. And in fact, when I did the measurements, it's about 10 times greater. That is, the distance in between the pivot and the center of gravity of the stick is 10 times greater than the distance in between the pivot and the hanging quarters. So pretty simple experiment, right? All you need is a mass standard. In this case, the mass of 4 quarters, let me see, 5.67 multiplied by 4 is about 23 grams, 22 2/3 grams. And then you just need these two distances. So what did I call this? R2 in between the pivot, the support string, and the center of gravity of the stick. And this, it's hard to see, but R1 is this tiny distance in between the quarters, or the output force, and the support, or the axis. So like I said, the weight is providing a counterclockwise torque. That is positive in Mathland. And the stick is providing a clockwise torque. That is negative in Mathland. Again, the right-hand rule. If you wrap counterclockwise, the thumb points out at you, that is positive Z. If you wrap clockwise, the thumb points away from you, and that is negative Z. It's better than clockwise and counterclockwise because it doesn't matter on your perspective. This, let me see, is counterclockwise, but it's clockwise for you, I think. Anyway, once you have these two distances, R1 and R2, and the standard mass, the positive torque and the negative torque add to 0. This is, where is it? Sort of the rotational version of Newton's second law. If there is no angular acceleration, the sum of the torques is nothing. All right, so positive plus negative gets you nothing. You add the negative torque to both sides, and then you just set them equal to each other. The point of this little puzzle is to figure out what is the weight of the stick. Well, the what did I say? The quarters were about 23 grams, and the ratio of distances, the big distance to the little distance, or excuse me, the little guy to the big guy is 1 to 10 approximately. And so 1/10 of the mass of the quarters, let's see, divided by 10, right, is around 2 grams or 3 grams, 2.2 grams. And that's all there is to it. Does that pass the common sense test? I have no idea. Does this look like 2 or 3 grams? Sure it is. It's balsa wood. It's super light. There are other interesting calculations that maybe we'll do next week. This is called the ideal mechanical advantage. All you have to do is measure the geometry of the lever system to predict the mechanical advantage, and the actual ratio of forces is the actual mechanical advantage. Load divided by effort, or output force divided by input force. Thanks for watching. See you in the next video.